back to our overview of machine learning methods. The decision tree falls within the classification category, which means finding description of several predefined classes and classifying the data sample or item or record or object into a particular class. That's what a classification is, and we have seen an example here before of this decision tree right here, where the tree helped us to make diagnosis whether the cell is a cancerous cell or a healthy cell. So it's a medical data. This right here is the root of the tree. So the tree is upside down. In computer science, the root is on the top and the leaves are on the bottom. So this is a node and it's the root node. We are asking a question: is the color dark or is the color light? In essence, half of the data that contains property color dark ends up on the left side of the tree. This means that from the root, the data is split in half. The one half is on the left side and it has property color dark. The other half is on the right side. It has the property color light. So essentially, starting from the root, the data is split into two subtrees. On the left side, we have the dark samples. And from here, the next attribute we use to split the tree is the number of nuclei. Either nuclei is equal to 1 or is equal to 2. If the color is dark and nuclei is 1, these data samples go onto the left side. Once again, we're splitting into two parts. The left side is nuclei equal to 1. The right side is nuclei equal to 2. So half of the data, and we don't know if it's half, but all the data samples have nuclei equal to 1. We end up on the left side of the tree, and all the samples have nuclei equal to 2 will be on the right side of this the dark subtree. Okay. The light subtree, same situation. Nuclei 1 on the left, nuclei 2 on the right. We are choosing here the nuclei. We could have chosen the tails instead of the nuclei, but we chose the nuclei. Same situation on the roots. We have chosen the color to split the tree. We could have chosen the nuclei. We could have chosen the tails. So how are we going to make this choice? Is the question. That's the whole philosophy of the decision tree model. How do we make the most pure split so we produce the best tree that gives us the results or the answer the easiest and the fastest way and the most accurate way? So the knowledge is on the bottom, on the leaves, the yellow underlined parts and where the tree ends. These are the leaves. So that's where the answer is provided. Question is the cell healthy or cancerous? So starting from the root of the tree, we traverse the tree in order to get to the knowledge or to the answer. Starting from the root, if we go to the left, the color is dark. We have 2 nuclei. This means that the cell is cancerous. If the color is dark and we have 1 nuclei and 1 tail, the cell is healthy. By traversing the entire tree, we obtain the answer to our question. All right, so let's see how are we going to build this this decision tree. So the tree is one thing, but the tree is usually sitting in a forest, which means that there could be other trees around, or there could be multiple trees. That is called a random forest. And you will see that when we go to program this, when we call the Python machine learning library, there isn't an actual decision tree, but there is a random forest that we need to call. Because the tree, we can get one tree from the forest if we only need one tree, or we can have a bunch of them working together as a forest. So let's see here. Induction of the decision tree. We will see a simple example with some colors and geometric figures. We will follow the ID3 algorithm, which is the most popular and algorithm that's been there for many years and it's currently being used. How we're going to choose the attributes? There are several measures from information theory, such as the entropy, that gives us the highest information gain that we would use in order to choose the best attribute to split the tree. So let's look at the data with some geometrical figures like triangles and squares. And we're going to build a decision tree that tells us whether the figure is a triangle or a square. All right. Here's another medical. Okay, so no, this one is not magical. This one is about using climate data in order to determine whether the question is it okay to go ahead and sail a boat in these conditions? If it's sunny or rainy, if the boat is small or big, and if we have someone with us or if we're alone. Is it okay to go ahead with the boat into the water? So the question is yes or no. The class attribute value to his two labels, yes or no. The yellow ones are the labels, these are the leaves where the knowledge is. Once we build this tree using parts of the data in our activity in our lab, we're asked to use 80% of the data. The remaining 20% would be used to test the model. So the model is already built. We can get an answer by traversing the tree. If the outlook is sunny, yes, we can go sail the boat. Now, if it is raining and there's no one with us and we're alone, we don't want to go alone into the water when it's raining. So the answer is no. Now, if we have a lot of people with us, if we have a big company, it might be okay to go into the water. So, by traversing the tree, we would get a decision support system essentially by providing us an answer what we should do. Yes, go ahead, or no, don't go into the water. Now, the remaining 20% of the data from our exercise, we're asked to use 20%, will be used to test the model. So this means that a new sample, a new object comes into the data, and the class attributes we would like to determine. This means if it is sunny, we have no company and a big boat. What is the class? Is the class yes or no? Is it okay to go ahead into the water? Well, the only thing we need to do to answer this question is just traverse the tree. So we're going to feed the first data sample into the decision tree model. Outlook is sunny, starting from the root. If the outlook is sunny, answer is yes. So we're done with answering the first question. The second one, what if it's raining? We have big company and a small boat. Should we go ahead or no? Class sail. So if it is rainy and we have a big company, the answer is yes. So that's how we would test. Now we have a question mark here. The question is, our tree says the answer is yes. Is it really yes? Is that what we have in the data? If so, then the model got it right and it's accurate. The answer is accurate. Same for the second one. As many data as we have in the 20%, we're going to compare the answer the tree provided with the actual class that's in the data and determine if it got it right or not and what is the percentage that it got it right, what is the accuracy of this model. So here is the algorithm for ID3 that we'll be following. This algorithm is implemented in a number of commercial data mining software. All of the software we see here we can use to build decision tree, such as Cart Assistant, C5. Orange is a free data mining software and visualization software. Here are some more real world medical data decision trees that tell us if patient is going to survive after a severe trauma. So here are some medical exams. They had severe trauma. If the medical exam that's on the top here value is less than 7.2, then their patient is going to die. If it is bigger than 7.3, they will survive. Anything in between, we need to split the tree further to determine the answer. Here we have another example with breast cancer, whether the cancer will reoccur or not. Degree of malignancy is used, tumor size, and the age of the patient to determine the answer. So let's see how we're going to build this decision tree. The algorithm is the following: to construct the tree from the learning set. If all examples belong to the same class, then we make a leaf and label it C. Looking back at our sailing the boat data, if all examples belong to the same class, make a leaf. We have that situation on the left side where it's sunny. This means all of the sunny objects, all the objects 1, 2, 3, 4, 5, 1 through 5,
Guys,
have the sunny property, also have equal to yes. I'll repeat this. Objects 1 through 5 have the sunny property, also have class label equal to yes. This means that we make a leaf and we're done with this side of the tree. This is what the algorithm is saying here. If all of the examples belong to the same class, then make a leaf and label it C. Otherwise, if that is not the case, select the most informative attribute and split the tree or partition the data according to the values of that attribute. To create a subtree. From there on, we just repeat this algorithm. If the subtree that we created has all of its example belong to the same class, then we have a leaf and we stop. Going back here. On the right side, objects 6, 7, 8, 9, and 10 have the rainy property. Looking at the class, some of them have a yes, some of them have a no. So, if that's the situation, we need to split this subset, this means 6 through 10, into two parts. Half of them have, I don't know if they're half, but some of them have the no property, and some of them have the yes property for the class. So we need to choose either the company or the sailboat attribute to make the split. We have chosen the company. If company is equal to no, then the class is no. And we have a leaf. This means all of the objects in the subtree of the rainy property that have a value equal to no for the company attribute also have a no for the class. So we have a leaf here. No company, answer is no. This specifically is object number 6. Rainy, no company. Class is no. Same situation for object number 9. Rainy, no company. Class is no. This means all the objects that have rainy and no company, the class is equal to no. That's why we have a leaf here. So we're done with this part of the subtree. Now, on the other side, it needs to be split further, and it is just recursively following the same algorithm. So that is the algorithm. We are creating subtrees. If all of them have the same class label, we're done. Otherwise, we split them further into more subtrees until we reach a situation where all of them have the same class label and we finish. Okay, so again, sunny outlook, temperature hot, humidity high or low, wind, is it windy? Then should we go outside and play? Play is for yes and N is for no. By using this data, we could produce a tree like this. This tree, we have chosen the one of the attributes, the outlook, and the sunny, if it is sunny, are on the left side, if it is rainy, are on the right side, and the knowledge or the answer is at the leaves. Now, we have chosen the outlook attribute. If we choose the temperature, instead of the outlook, we end up with a tree that looks like this. So again, we have leaves that provide us an answer, yes or no, play or no, do not play. But this tree here is much bigger, much deeper, and much more complex than the previous tree. So which tree is the better tree? The better tree is the simpler and the smaller tree because we can get to the answer much quicker and easier. First of all, second of all, building a smaller and tree is less computationally expensive, so it is quicker for us to build the model and easier. Traversing and getting the answer is quicker and easier because we only have to ask 2 questions in order to get to the answer. This tree is of depth level 2. Only 2 questions and we're done. We get to the answer. The other one is depth 5. We could have to ask up to 5 questions before we get the answer. So the idea is we want to build a tree that looks like this. And for that reason, we would use some measures such as the entropy. That's an information theory measure. Some statistical measures can be used, like the X square error or the Gini index. No matter which ones of those do we use, we end up with a very similar answer. The idea here is to maximize the information gain. So the information gain is equal to the information minus some residual information. We will be computing this residual information in order to choose the smallest possible residual information so that the gain is maximized. What this picture is showing here is no matter which measure we use, the entropy, the Gini index, or the statistical error, when do we have the best situation and when do we have the worst situation? The worst situation is right here in the middle of this graph. That is P probability 0.5. This means pure randomness. 50-50. Split flipping a coin, heads or tails, 50-50 chance. When we have a 50-50 chance, the situation is the worst for building the decision tree because we're trying to determine what the answer is. If we get to a situation where we don't know what the answer is because the chance is 50-50, pure randomness, that's not good. What we want to have is we want to be sure what the answer is so that the probability needs to be like 100 or 100% or something that's close to 100%. So here's the situation. The best situation is when we know what the class is and we have a leaf. That is, yes, go ahead and sail the boat. Yes, go ahead and play outside. This means if we split the tree in this way, all of our samples are of the same class. So if we have 6 samples, 6 of them are of class 1, and no matter which measure we compute, we'll end up with a value of 0 for that measure. That gives us the most pure split because there is no residual information and we have the highest information gain. All of the objects belong to the same class. For that part of the tree, we're done, we have a leaf. Now, if some of them belong to one class and others to another class, we would have to compute those measures and decide which attribute to use that will have the smallest residual information. If we choose an attribute, let's say one object is in a different class, but most of them out of six, five of them are in the same class, that's pretty good, right? We are close to probability of 100. Now, the worst situation is when half of them are in one class, half in another. That's when we have that pure randomness 50-50 chance. Out of six, three of them are in class 0, three of them are in class 1. And all the measures, the entropy, Gini index, X square, will give us this 50-50 situation, 0.5. That's what we would like to avoid. That's the worst situation. So let's see real quick how we can build the decision tree with using these triangles and squares. We would like to determine whether the shape is a triangle or a square. And we have some attributes such as the color, the outline, and the dot. So we're going to compute the probabilities and the information gain. We got 14 objects. 9 of them are squares and 5 are triangles. So probability of having a square will be 9 over 14. And probability of having a triangle will be 5 over 14. The information gain is by using this logarithm base 2 formula, 0.94 bits. Out of this information, we need to subtract the residual information for each attribute in order to determine which attribute to use to split the tree that will give us the highest information gain. So we're going to do some computations for each attribute using the entropy. The entropy is this logarithm base 2 formula that we have seen. If we are to use the color, the information, the residual information will be 0.69 bits. If we are to use, so the gain for the color would be the highest out of all the attributes. We're going to do this computation for all attributes. The gain of color is 0.2. The gain of outline is 0.1. The gain of dot is 0.04. So whichever attribute gives us the highest gain is the one that we will choose to split the tree. So heuristic is use the attribute with the highest information gain. So because of that, we choose the color and we end up with subtrees, each of the same color. The red is here, the yellow is here, and the green is here. Now with the yellow, we have a leaf because all of the objects are of the same class, all of them are squares. And we are trying to determine what makes an object to be a square and what makes it to be a triangle. Since all the objects of yellow ones are squares, we got an answer here. If the object is yellow, it's a square. We're done. Now these other ones have a mixture of squares and triangles, so we have more work to do to determine what is the class. Again, we're going to compute the information gain. Whichever attribute give us highest information gain, that's the one that we should choose to split. Now the subtrees. So in this case, the gain for outline is 0.02, the gain for dot is 0.9. So we should be choosing the dot here and on the green one, the outline. Once we do that, we end up with leaves everywhere. Here is one leaf, all of the objects are triangles. Here's another leaf, all the objects are squares, and so on. So if the color is green, the outline is dashed, we have a triangle. If color is green, outline is solid, we have a square. So this is that very nice tree that we have seen earlier. That is a simple tree of depth 2 that allows us as quickly as possible to get to the answer. So in a big data scenario, if we want to process some big data, we can have a cluster of machines where each machine would have its own tree and give some parts of the data to that tree, have them in parallel process each tree on each machine at the same time. In this way, we're having a forest of trees, or what is called a random forest. And once the trees are done, we can collect the results and combine them together. This is showing an actual decision tree built with a software from the machine learning iris dataset, which is what we have in our lab today. The iris dataset is a set of flowers that tells us what makes the flower to be of Iris setosa, or what makes it to be an Iris virginica. And we have the petal length, and the petal width is the only attributes that we have. Using those attributes, we need to build a decision tree that tells us what is the class of the flower. So we're going to use 80% of our data to build our decision tree that's going to describe the Iris setosa flower and the Iris virginica flower. And then 20% we will feed a new flower and ask our tree, what kind of iris is this one down here? That ruby red iris right here. Is it an Iris setosa or is it an Iris virginica? And the tree needs to answer this question. That's how we will test our tree. Okay, so let's look at the code for this.